Session 2, which will focus on sustainable energy storage through next generation fuel cell technologies. This topic is of great importance in the global quest for clean and resilient energy solutions. Ladies and gentlemen, it is my pleasure to introduce our distinguished speaker for session 2, Dr. K. Ramya, Senior Scientist and Head, Center for Fuel Cell Technology at the International Advanced Research Center, ARCI, Chennai. Dr. Ramya holds a PhD and brings more than 2 decades of research experience in the field of hydrogen and fuel cell technologies. Her domain expertise span polymer electrolyte membrane fuel cells, PEMFCs, direct methanol fuel cells, polymer electrolyte membranes, hydrogen generation, regenerative fuel cells, electrochemical CO2 conversion, and electrocatalyst development. Throughout her career, she has authored numerous peer reviewed journal articles and presented at key international forums. Her work has contributed to membrane development, fuel cell component optimization, and novel electrocatalyte design, all critical for advancing sustainable energy systems. Today, she will speak to us on sustainable energy storage through next generation fuel cell technologies, bringing her deep insight into how fuel cells can play a pivotal role in energy storage and sustainable development. Please join me in welcoming Dr. K. Ramya to the stage. Ma'am?
Yeah. You can hear me?
Yes.
Thanks a lot for your introduction. I would like to thank Dr. Lakshmi Bai and Dr. Anisha and all for thinking about me for presenting this topic actually. And I would like to thank the other organizers also for bringing me to this forum to give a lecture for the FDP. I'm sharing my presentation. Just you are able to see my presentation?
Yes, ma'am. Yes, ma'am.
Yeah. Full screen also now?
It is, yes, now it is full screen.
Yeah. So, good evening, everybody. So, my topic for today's presentation is sustainable energy generation through next generation fuel cell technologies. I would like to talk about my center actually. I come from this place called Center for Fuel Cell Technology that is located in Chennai, and it is one of the centers of excellence of International Advanced Research Center for Powder Metallurgy and New Materials. The head office is in Hyderabad, and most of the centers, there are about 11 centers of excellence, and most of them are in Hyderabad. Only Center for Fuel Cell Technology and Automotive Research Center is in Chennai. And we are a government R&D institution. We are an autonomous institution under Department of Science and Technology. And we do work for, we do research and development for strategic and non-strategic sector. And our main aim is to technology transfer, transfer the technology to Indian industries. We also have an incubation center where industrial startups or industries can come and set up the technology where so that we can handhold them and to further the technology. And then we also have joint centers with our international partners, and we collaborate with many international and national research labs. Our main motto is to translate the research to technology. Whatever we are doing at the lab level, we should finally end up with a product which is useful for everybody. So at our center, actually, the research areas are focused on fuel cell technology, mainly fuel cell technology. And even in the fuel cell technology, it is polymer electrolyte membrane based fuel cell technology. We do have some research interest in alkaline fuel cell, which is an emerging field where a lot of materials and cells are currently being developed. And because fuel cell technology requires hydrogen, so we also branched into hydrogen generation. So we look at electrochemical method for hydrogen generation, basically water electrolysis technique, and also alkaline membrane based water electrolysis technique. We also have a PEM based electrolysis technology, which we call it as electrochemical methanol reforming, which is basically a methanol based solution which is reformed to give hydrogen. We have done some work on the chemical method of generating hydrogen, which is basically you take a sodium borohydride. From borohydride, you have to release the hydrogen in a controlled manner. This technology we developed so that borohydride is easier to transport than gaseous hydrogen. So once you generate hydrogen, you cannot directly connect it to fuel cell. You need to have a storage system. So we earlier used to do some work on low temperature alloys and carbon based materials for storing the hydrogen. Currently, we only integrate the commercially available hydrogen storage system with our fuel cell. This is for showcasing the technology in various applications. Having developed all these materials, we have got what is called spin-off technology. Basically, these are materials that we have developed in all these things like supercapacitor. We can use those materials in supercapacitors or metal air batteries, which are similar to PEM based fuel cell, where the air electrode is same. The only hydrogen electrode is replaced with a metal there. And we also do some redox flow batteries, basically vanadium based redox flow batteries. And so coming to the technology as such, what you would have like the previous lecture, you would have heard about energy storage systems. These are basically capacitors, supercapacitors, or batteries actually. So when do you use when do you select how do you select which product actually? So if you want a lot of energy for a short span of time, you would go for capacitors and supercapacitors. Battery gives you for a longer duration, so you can use, but however, the power density will be less compared to capacitors and super. So if you want a short burst of energy, like you want to crank a vehicle, and that time when it draws more current from the battery, it is not very good for the battery. Suddenly you are drawing more than what is the rated capacity. So you use a supercapacitor or a capacitor in conjunction with the battery. So once the cranking is over, battery takes over. So batteries have a limited capacity, in the sense that the energy being stored within the battery. So once that energy is consumed by discharging, you do not have any more capacity for the vehicle or whatever as a power generator. So you have to recharge the battery, and that is likely to take several hours, or depending on the type of the battery that you are using, it is likely to take several lot of time. So you use a fuel cell when you require power for a long time. See, because these are in fuel cells, the hydrogen and the air, of course, is stored outside the cell. It is not within the cell. So whenever you require power for a large outage, 8 hours, 12 hours, or more than that, when you cannot have so many batteries, your battery will be too much actually, if you have to store for so many hours or days of performance. So you use a fuel cell. What is the advantage of fuel cell? Because you use hydrogen, the emissions are very less. Like when you do wood or coal or oil or natural gas, the carbon emissions are higher. But when you use a hydrogen based fuel cell, the emissions are nil, because only hydrogen and oxygen are combined to give water. That is the only byproduct. So fuel cells are of many types actually. Like I said, we are doing polymer electrolyte membrane based fuel cell. You have other types of fuel cell also, phosphoric acid, molten carbonate or solid oxide. It all depends on what is your working temperature and what is your electrolyte basically. So if you are looking at low temperature fuel cell, an alkaline or a polymer electrolyte membrane based fuel cells are useful because these operate in the temperature range of 50 to 80 degrees centigrade, and they can be easily started. They are amenable for low temperature startup, and they are quite well developed in the sense they are commercialized also. There are buses running with polymer electrolyte membrane fuel cell, and they have a good efficiency, about 50%, and you can have hydrogen or methanol as a fuel. So if you are looking at working temperature of 160 to 200 degrees centigrade, phosphoric acid is the go-to technology. The advantage of going from low temperature to higher temperature is that your hydrogen need not be very pure. In case of PMFC, your hydrogen has to be more than 99.999%, 49s actually, 49 or 59 pure. Then only your fuel cell will have a long life. So if your hydrogen is from a reformer where it can contain some amount of carbon monoxide, like it contains few ppm of carbon monoxide and all, it is better to go for phosphoric acid based technology, which can accommodate this kind of, because the higher the temperature, the catalyst can withstand this kind of poisonous gases and performance can still be retained. And molten carbonate and the solid oxide fuel cell are technologies which work at very high temperature. You have higher efficiency because you have the heat that is generated is at very high quality. You can have subsistence of, you can have combined power and heat generation. So those systems, when you attach, then you have your efficiency increases. So they are very good, and you can use higher percentage of carbon monoxide, or you can use natural gas also in some of the cases. And so what is a fuel cell? Basically, it is like an electrochemical cell, just like a battery. It has an anode and a cathode, and only this thing is that chemicals are stored outside the cell and fed into the cell when required. So there is no self-discharge kind of a thing in case of fuel cell, because you are feeding the chemicals only when it is required. So chemical materials are stored outside the cell, fed into the cell, react in the cell electrochemically, and so they convert chemical energy to electrical energy. So in the diagram, you can see a typical fuel cell, which is a PEM based fuel cell. And you can see that hydrogen is fed into the anode, and hydrogen is fed to the anode, and oxygen or air is fed to the cathode. At the anode, the hydrogen is split to form two protons, which pass through the electrolyte and react with oxygen to form water at the cathode. And the electron movement gives you the electricity. So a typical single cell assembly requires, so because you are feeding gases, you have to have some method to feed the gas into the cell. You have to ensure that the cell is leak proof, the gas does not flow out, and it is useful for making the reactions. So all these things you have to ensure. A typical cell has an end plate, a current collector, a gas distribution plate, a membrane electrode assembly, which is the heart of the fuel cell, where, like I said, an anode, a cathode, and the electrolyte are present, and also some kind of sealing system so that the gas does not leak actually. So what is the difference? Like I said, reactants are stored inside the battery. Here it is outside. In battery, there is a possibility of self-discharge. There are no self-discharge here. And battery is grid dependent because you have to recharge the battery. So it becomes grid dependent. Here, since everything is stored outside, it is grid independent. And life cycle of a battery, you would have seen some 500 cycle, 1000 cycle, depending on the type of the battery. the life cycle of the battery is limited. Here you are getting the power whenever you feed the gases into the system, and a typical life of a stationary fuel cell is more than 40,000 hours actually, and for a vehicle system it is more than 10,000 hours. So uh, life is not limited by the number of cycles actually. So, like I said, why do you choose PEMFC? Because it is scalable actually. So you can have cells depending on whatever the capacity you can design the capacity from, for low power applications like a portable application to a power station. So you can do multiple cells depending on how much ever power you require, and they are efficient, and they have more than 40 to 60% efficiency, and they are reliable, and also their response time is very fast. So if you look at the fuel cell, this PMFC is applicable for all kinds of application, from low power to high power, 10 megawatt also it is available. PAFC normally is employed when you require, it is not for, a day-to-day home application where you can start at a low temperature. So normally they are used as a stationary power at a very high kilowatt level. Both molten carbonate and SOFC are also for stationary power at a large scale level. So whereas PMFC is used for all backup, material handling, buses, distribution system. So it has a lot of flexibility across all the power ranges actually. So a typical application for a fuel cell, like I said, it can be for consumer electronics to small portable military equipment, battery chargers. It can be for any of those things. And for the transportation application, you have seen already our minister driving a Toyota Mirai car. So you have a car, you have heavy duty vehicle application, and you also have, you can also use it as an auxiliary power for various applications in vehicle. And on the stationary, you can have distributed power generation. You can do combined heat and power for home and other applications. And as a backup power, as for telecom application, you can do immense number of applications are possible with typical fuel cell. So how much voltage does it in an average fuel cell, any fuel cell, single cell generate? So theoretically, it can generate 1.21 volts actually. However, because of various losses, you will get only over potentials and losses because of the catalyst, or what is called as an activation loss. Your fuel cell will start at somewhere at 1 volt. But at 1 volt, you will not get any current. It's only an open circuit voltage. So once you start drawing the current, your performance, the voltage comes down. A typical fuel cell operates at around 0.7 or 0.6 volts actually, and and remains constant. You can draw current. If you see here, you have a region where the voltage is more or less constant, and then so that is the region where you have ohmic losses due to resistances due to the membrane, and contact resistances. All these things come at this point, and then once you start drawing still more current, the voltage starts to fall suddenly actually. So this is the region what is called as mass transport region, where you are not able to feed more oxygen or more hydrogen at that period in a short span that it is required. So you operate the cell in the ohmic region actually. So, like I said, potential applications are many: small material handling, or large material handling, off-site trucks, portable backup power generator. Sure, nowadays, Kerala is the first one to demonstrate a boat with PEM fuel cell. So we have now recently in the land, actually trains, buses, and long-haul trucks are the main application. And India has recently completed testing of its first hydrogen-powered fuel cell train that was built in Chennai only. and the prototype will run between 2 points in Haryana actually, and the government proposes to deploy more than 35 such trains on the heritage and the hill routes to reduce the emissions. So a little bit about the history of the fuel cell. So it was in 1799 when the French scientists said that hydrogen can be used as a force that can be applied on all the machines. And then the first cell was a water electrolysis cell way back in 1939. And then in 1959, there were fuel cell prototypes which were sent on the Apollo missions. And then in 1980s, car maker Mazda and Toyota and all have launched a hydrogen-based vehicle. Toyota has this Mirai vehicle, which is a car. And now there are a lot of train and so many other applications are also there for hydrogen. This is basically for hydrogen for mobility application, whatever I have given. So having seen all these things, what are the major materials and components that are required? So you need like I said, because it's a polymer electrolyte membrane fuel cell, you need a membrane. And then there is anode and a cathode. Both require catalyst. So you have to break the hydrogen to H2 to H plus ion. So you need some kind of catalyst. Similarly, oxygen has to react with hydrogen H plus ion. So you need some catalyst for oxygen reduction reaction. So both catalysts are mostly applicable in PMFC. Is a platinum based catalyst, noble metal based catalyst. And then you have what is called the gas diffusion layer. So gas has to be supplied across the electrode fully actually. So what you require is a substrate which can distribute the gases across the catalyst. So what is called as the gas diffusion layer. Then apart from that, you have flow gaskets. Like I said, gas should not leak, so you should have gaskets. Flow field plates are there, current collectors are there, end plates are there, some kind of clamping mechanism to ensure that gases do not leak. So what are the electrochemical techniques that you use in a fuel cell? So you have, if you have a catalyst, you want to study its properties, how good your catalyst is. You do what is called the cyclic voltammetry, which tells you about the oxidation and the reduction reactions and what kind of activity is there for hydrogen oxidation or hydrogen oxidation, oxygen reduction. So cyclic voltammetry test is what you do. So then you can also do linear sweep voltammetry. This is again a variation of the cyclic voltammetry only. So to study in detail about the part reaction. Then you can do, you need to know what kind of resistances each of the cell component is contributing. So you do electrochemical impedance spectroscopy. Then you also have, because the membrane is acidic, you have corrosion of the component. So you do the corrosion studies. Apart from that, you can do how good your electron transfer is, rate of the electron transfer. You can do electrochemical reaction mechanism, transport properties, all these things you can do. By doing all these studies, you can study the catalyst, you can study the binding agent, you can study the co-cation impurity that are there. If you are doing a direct methanol kind of a fuel cell, you can study how much methanol is crossing over across your membrane. You can study the poisoning. All the studies you can do with doing these electrochemical studies. And so what are the main driving forces in PMFC research, or what is it that you want to achieve with the materials actually? So you have two main things. One is to improve the technology. The other one is to reduce the cost. So the major component, if you see the cell component, there is a catalyst, there is a membrane, there is a bipolar plate. Bipolar plate is what is used to distribute the gases. So these are the three major components. So you see there will be a lot of studies on catalysts. many papers are there on catalysts, platinum alloys, platinum supported platinum, all kinds of pure platinum, all kinds of catalysts are there. And then on the membrane, you won't, there are also many studies, but most of the PMFC research is based on Nafion as the membrane, which is a trademark component from DuPont. And most of the research would be carried out with that membrane. So not much, because this is a fluorinated membrane. I'll come to the reason why not much research on that. And then you have bipolar plates, that is another component. And apart from this, all the other components are minor, so I have put them in the together. So the heart of a fuel cell is basically a membrane electrode assembly, which is, like I said, there is a membrane and there are two electrodes. So how well you form this membrane electrode assembly decides the current that you can get from the fuel cell. So let's first look at the first component, catalyst, which is, like I said, mostly noble metal, that is platinum only is used as a catalyst, because we have two different atmosphere actually. One is in first it is an acidic environment. Second, you have hydrogen, which is highly reducing, and you have on the other side oxygen, which is highly oxidizing. So for that kind of catalyst, platinum is the best catalyst, because it is stable. It is you don't see platinum getting oxidized and this thing. So, and if you look at the volcano plot, or what is known as the volcano plot, platinum has the highest activity for these kind of reactions. So that is the most commonly used catalyst. Then this platinum, you can do pure platinum actually as particles, or what is called as platinum black, or you can do supported on carbon. This, when you support it on carbon, the platinum particles are in the range of 2 to 4 nanometer, and chances of it coalescing back during the reaction are very less. So most of the work research is on platinum supported on carbon. And again, like I said, how do you reduce the cost? You can achieve by improving the catalytic activity. For that, you can do either particle size reduction of the platinum, like from there will be 20 nanometers, 10 nanometers. If you go to 2 to 4 nanometer, like that, you can get better activity. Or you can have your dispersion in the slurry before making the electrode. So that also makes a lot of difference in what kind of performance you get. And other than that, there are also research on non-noble metal based catalysts. However, these are not yet commercialized, because like I said, the best catalyst is platinum. So most of the research is on platinum. And the second thing is you can do is to improve the durability. So if your catalyst works for a longer time, then also you can reduce the cost of the stack. Like instead of 40,000 hours, if you are able to run the cell for 100,000 hours or something, your cost also reduces on that. So here you will have to study agglomeration, coarsening, and catalyst support, on degradation, non-carbon supports. These are the main things that you have to study in this. So if you look at the catalyst electrode, actually platinum is very expensive, and out of all the catalysts that you have quoted, only 20% of the catalyst is active. So all these catalyst dispersion, particle size reduction, all these things become important in the 20% actually. And you have to adjust the composition, everything, get maximum performance. And if you look at here, you can have pure, there are, like I said, with platinum on carbon, you are adding carbon, which is non reactive actually. So there can be resistances because of these carbon support. So there are people who work with pure platinum and platinum in various shapes, octahedron, tetrahedron, and all that. And also you can also do composites, where like here in this this thing, where you can see pure platinum gives one kind of performance, and platinum on carbon gives a separate performance. And then you have a composite with graphene and multi-wall carbon nanotubes, you get better performance. So the second component is polymer electrolyte membrane. So like I said, most of the this thing is Nafion is the main material, which is a DuPont trademark. And why it is very expensive is because you start with a gas, tetrafluoroethylene gas actually, and there are more than 7 steps to finally to arrive at the membrane actually. So all these use of these fluorinated material, that is what is making the driving the cost component. And because it is a monopoly actually. And what you require is good barrier property. The gases, hydrogen and the oxygen should not mix, and it should have very good mechanical strength, thermal and chemical stability, and it should have very high conductivity for transport of this proton. And basically they are all ionic polymers with high conductivity. So what are the substitute for Nafion? Lot of studies have gone in many other aromatic polymers, and they have sulfonated these polymers and used as polymer electrolyte membrane. However, their performances are not very good, and also their stability because like I said, oxidizing and reducing environment. So that is also not very good in these kind of atmospheres. As a result, they are not much commercially known. The only other membrane to make it to commercial is that polybenzimidazole based membrane, but this operates in a medium temperature. Like I said, like it is like phosphoric acid, PAFC fuel cell. Here also phosphoric acid is doped onto this membrane to achieve good conductivity. And this membrane has very good strength, and also what people call as HTPEM, high temperature PEM fuel cell. This is so operates around 160 to 180 degrees centigrade. So this membrane can also be used. If you want to start at low temperature, of course you have to go to Nafion. The third component is the bipolar plate. Basically, these are graphite. If you see here, there are different kind of patterns on each one of these cells. So this is a continuous cell where it is like a serpentine flow. Then you have these kind of columnar flow patterns. Then you have straight channels. You can have many such flow. Your whole idea is to ensure that the gases are distributed across the whole plate completely, and your current collection is very good, so that your performances are good. So one of the major difficulty with graphite is that it is very high cost, and these designs are basically machined actually. You have to use a CNC milling machine, and you have to generate these designs. And that makes these plates actually, these graphite is basically brittle. What you are looking at material properties, high electronic conductivity, low corrosion, and gas diffusivity should be low, good chemical compatibility, low cost, low weight, and all that. But like I said, graphite is very expensive. So if you want to reduce the cost of the bipolar plate, you should look at alternative bipolar material, basically a polymer composite or a metal plate, which can easily be stamped, where the design can be found by stamping or hydroforming or other techniques. Or you can use graphite based material, which is exfoliated graphite, which can be compressed. You can do compression molding on these kind of materials also. So if you do a noble metal based plate, then they are non-corrosive, nothing. They are very good manufactured. You can do thin plates, but they are very, very expensive. So what you do is you go for a non-noble metal like aluminum, magnesium, titanium, or stainless steel or alloys, and then you try to do a high corrosion resistant coating on them. Otherwise, the metals that will be leached out will contaminate your membrane actually. So you have to do a corrosion protection coating, Basically, they can be done by various techniques like electroless plating or electroplating, vapor deposition, and all that this thing. So if you look at here, see graphite, very good conductivity, but cost is also very high. There are many pros, which is very good. It suits all our application. However, they become very expensive and they are very heavy also. Conducting plastics, conductivity decreases because you have a plastic component in them. The cost comes down, of course. They can be easily injection molded, but the problem is the low conductivity. In case of metal, the conductivity is very high, cost is also very low. You can do thin, lightweight, very thin plates actually. However, you have to do corrosion. Corrosion is the main problem, so you have to do a coating. So here is an example where you have comparison between graphite and treated metal. So you can see that the power density when you use metal-based bipolar plate is very good because of the conductivity and other properties. So at ARCI, what we have done is we have developed exfoliated based graphite plates. These are much thinner. They are done by compression molding, and we can do from various sizes. There are many designs, and we have done various type of plates actually. So let's come to the now look at the component. We have seen the materials. Now look at the components. So you have a catalyst. I told you like we have to do a gas diffusion layer, and then you have to make a membrane electrode assembly actually. So for that, so a typical, like I said, electrolyte is the membrane, and the catalyst is coated either onto the membrane or to the gas diffusion layers. And then all the three are made into a single component, what is called membrane electrode assembly. And a typical membrane electrode assembly looks like that, and there is a gasket here which ensures that the gases do not leak actually. So you have you can do, you have to apply either some kind of adhesive to make sure that they stick to the bipolar plate, or you have a gaskets which are there are channels where you can place the gasket, and then you have to pre-press the membrane electrode assembly into a press, and then you have to assemble the current collectors and ensure that the gas does not leak by using a o-ring plate or an end plate, and then you end plate, and then you tighten them with bolts and nuts so that there is no leakage of the cell actually. So this is how a typical cell, where multiple cells are assembled. Like I said, individual cell will only give you 0.6 volts. So if you want to have a 12 volt or a 48 volt application, then you have to have multiple cells in series actually. So you have to have some mechanism and to assemble the cell and then clamp them together. So once you have assembled the stack, what you do, you can do studies with, vary the temperature, pressure to see what is the maximum performance that you can get out of your stack. And if you run a cell, you will see that the dynamics and the performance are influenced by the reactants, how much reactant flow excess you are giving, what kind of flows you are giving. If you give excess flow, then your membrane is likely to dry and performances will reduce over a period of time. How well you manage, because when you run a fuel cell, you will see that equal amount of heat is also generated along with the power. So you have to have some mechanism to remove the heat. Otherwise, the membrane will dry. And also, and so what we do is the gases are humidified. Gas streams contain some amount of vapor. So water content, how much water content is there when you give it to the cell, all these things are monitored actually. So these are the various parameters that you monitor. What is the gas flow level, what is the humidification temperature, what is the stack voltage and the current that you are generating. Individual cell voltages you have to monitor, and you have to see the stack temperature, water flow rate, humidity, everything you have to monitor. So if you look at the technology as such, what we have seen is we have seen the materials, we have seen how to make the components, membrane electrode assembly, how to assemble, make it into a single cell, and then you do multiples of single cell, you come to short stacks or a large stack. Now, having done all these things, you have to have what is called the balance of system. See, you have done the stack, but you have to have some method to supply the air, the hydrogen, and coolant supply. And you have to have some, like I said, you have to manage the heat. So you have to have some thermal management system. And fuel cell generates DC power, and it's a variable DC. So, like I said, open circuit voltage is 1 volt, operating voltage is 0.6. So that means your converters should be able to accommodate this large variation in the voltage. So 50% variation in the voltage, it should be able to accommodate. So these are not your normal inverters or converters. So you have to have special kind of power system, power management system. And then you have to have control system to all. If you want to do a remote monitoring or something, you have to have some kind of control system. So when you integrate all these things, you get what is called as a fuel cell, that integrated fuel cell system. So that becomes a product which can be tested in real time application. So if you look at the balance of plant components, basically first you have to have air and the fuel supply system. For air, you have to have some kind of compressor, air compressor, and for fuel supply, you have to have some kind of valves, basically either proportionate valve or some mass flow control system kind of thing you have to have. And for thermal control, you have to have these humidifiers for ensuring that the gases are humidified before passing through the cell. And you have to have some kind of heat exchanger to remove the heat from the stack. And radiator fan assembly, if you want to do a closed loop system, then you have to ensure that the heat is dissipated into the atmosphere. And for this, you have to have some kind of coolant pumps, air radiators, all these things, power conditioning systems, all these are required. And if you want to recirculate the hydrogen, you have to always give 10% excess or 20% excess, so that the water does not stagnate within the cell also. So if you want to recirculate the hydrogen, then you have to have some kind of recirculation mechanism, a recirculation pump or a ejector kind of a system. So all these things are required. So many auxiliary components like blowers, pumps, valves, all these things are required. You have to ensure that the hydrogen is always, the feed gases do not stop. So you should have kind of sensors to sense the hydrogen presence, and it should also not leak. So you should have leak detectors and regulatory valves. All these are required for a complete system actually. So, like I said, one of the main reason is for in PA, one of the main component is that the membrane always has to be humidified. Otherwise, the conductivity of the membrane decreases, and the performance will decrease. So the gases have to be humidified for that. There are different methods of humidification. You can do an external humidification, or where the gases are preconditioned before sending them into the cell, or you can do an internal humidification where within you modify your electrode structure in such a way that the water produced is retained within the cell and is useful for maintaining the humidity of the membrane. So these are the various conventional method you do. You bubble the gas through a column of water, or you use an enthalpy wheel based humidifier, or you have an evaporator in the chamber where the water will be evaporated and steam can be injected within the system. All these things are possible. Other type is possible is a membrane humidifier, where you have a membrane. On one side, you have a water water, or on the other side, you have gas, and across the membrane, the gas picks up the water and then humidifies the inlet gas to the stack. And this is the kind of system we had developed, and then we had these are based on PVA based membranes, and we had developed water to air water to gas humidification system, and we had studied the various properties of all the membranes and how it works, and how many cells are required for a particular kilowatt of fuel cell and everything. Other thing can be gas to gas humidifier. In this, what you do is the oxygen side is where the water is produced. So you have that water rich outlet gas as one of the components passing on one side. On the other side, you have a dry gas, and you use a porous membrane. So water will diffuse across this porous membrane and the gas will be humidified. So this is meant basically for air cooled stack where there is no coolant water available. And this is the way I said, the membrane is a porous membrane and the water is moves across the membrane, and the dry gas gets humidified and you get a humidified gas actually. So for such kind of you use expanded Teflon based membranes actually. These have more than 80% porosity, and these can be used for making these kind of humidifiers. And again, you study on these also, you have to size your humidifier according to the amount of gas that you are giving. So you study with respect to the flow rate, what kind of humidities you can get, and with respect to temperature, and with respect to the whether what kind of temperature outlet that you are getting from your stack. Based on all these things, you can size your humidifier. And then you finally be integrated. This is a PM fuel cell stack, and this is a humidifier, and we integrated it for performance studies. So the last component, like I said, is a heat exchanger. You have to have some kind of thermal management system to remove the heat from the fuel cell. And if you see, look at the performance actually for a fuel cell, the operating temperature is about 60 to 70 degrees centigrade. As a result, what happens is your delta T is very less. Ambient water temperature will be around 40, I mean, once it comes out of the fuel cell, it will be some 30 to 40 degrees centigrade. And the maximum operating temperature is around 60. So under those circumstances, your performance will be very less, because the delta T is very less. You will not be able to cool the stack actually. So once, if you can improve your performance to above 70, 30, 20, 30, 40 degree, if you are able to have a delta T difference between the coolant and the outlet, then your performance also will increase, and also you will be able to effectively use a heat exchanger to remove the heat. So those are also another kind of systems that are being developed for fuel cell. So basically, what are all the things that you have to look at? Amount of heat that is you want to reject from a fuel cell, and what is the voltage of the stack, number of cells. All these things you have to know before designing a heat exchanger. So in a typical stack, what happens is, from the stack will give you equal amount of heat. So part of the heat is normally used for humidification of the gases, hydrogen and air, and then it goes to the water reservoir, and from the reservoir, it goes through the heat exchanger to the reservoir, so that the all the heat is removed actually before it is pumped back into the stack. So here is an example where, about if you are generating 2.3 kilowatt of heat power, about 2 to 2.5 kilowatt of heat will also be generated, and part of it, like 0.7 kilowatt, is used for this humidification, and the rest 1.8 kilowatt has to be removed through the heat exchanger. The last component is the control system, because based on this amount of hydrogen and air that you are giving, your performance will depend. If you are giving very high flow rate, then the membrane will dry, and your performance will decrease. So you have to have some control on the stoichiometry of the gases. So you have to have some proportional integration and controllers, and various kind of controllers are required. And you have to, for controlling the system, you have to have some kind of feedback controller, so that when, depending on the current, you give the amount of the gases are regulated. you don't want excess to, and then so that you don't have to recirculate more also. All these things have to be taken care of while operating a fuel cell. So what are the target properties, and what should be your stack performance and all these things are given by USDOE. They set the values for various auto systems and all, how much catalyst, but how much you are able to come closer to these kind of values is what is more important. How much platinum you should use for per kilowatt, what is the net power that they are looking at, what kind of membranes, air stoichiometry and heat, all these things are mostly defined actually, like what is the thickness of the membrane, and whether you are how well you are able to come closer to these values determines the performance and of your fuel cell. So similarly for the material, not only for the materials, they also give you target properties for the type of air compressors that you have to use, and radiator, like aluminum radiator, that so that the water the weight is less, and what kind of coolant, what kind of pre-filters, and all these things that are needed, like air humidification is done by plate and frame type humidifier, and then you have to recirculate the anode gas, so pulse ejectors are used, and then whether you recover the water from the exhaust gases, all these things are also, you can look at DOE site, then they'll give you various parameters. So let me come to what we are doing at ARCI. So at ARCI, we are developing these catalysts. We have developed one platinum on carbon-based catalyst. This is on what is known as the functionalized acetylene black. These catalysts are very high, have very good durability. This technology we have transferred to one company. And like I said, we have developed graphite plates, which are based on exfoliated graphite material, and we have many designs, and we have these plates are also made for us by a company, and based on all these things we have made various products, from 1 kilowatt of fuel cell to we have done up to 10 kilowatt of fuel cell in a single stack, and 20 kilowatt is a multiple of two stack actually. And in the portable size, this thing also we have made a small fuel cell, which is for charging application. And we also have something in the 0 to 300 watts kind of a thing for various charging and other application. In the transport, our stacks are not or slightly bulky compared to commercial stacks. So it was only a demonstration for, as a range extension we have done for a Reva car. We also did a fuel cell go-kart and a scooter and a three-wheeler and three-wheeler, two different types of stacks were used actually. And we have done some demonstrations also. We have demonstrated our system at Neyveli Lignite Corporation, at Gas Authority of India. Then currently what we are doing is doing an automation of PM fuel cell stack assembly. So where we start from materials to actually final stack. So various lines are there, carbon line, carbon line is there. Then we have Nafion line where the membrane is processed. Then you have an assembly zone. Then you have a stacking zone. So all these things we have developed. So so having seen all these things, what you can see is fuel cell are one method of achieving your net zero targets actually, whereas hydrogen and oxygen mix only to give you product is only a water. So these are one method of achieving your net zero targets. And fuel cell as such opens up research it's a multidisciplinary research. You need you have seen use of chemical engineers, metallurgists, material science, electrochemists, so many power control, so many different kind of people have to come together to make sure that your stack works. So there is opportunity for all different kinds of specializations and uh, and thank you. So if you have any questions, you can ask me.
Any queries from the participants?
Participants, you can unmute your mic and ask your questions, or otherwise you can drop your query in the chat box. Ma'am, I would like to understand the versatility of fuel cell technology. Considering both the residential and industrial application, how effective are fuel cells in meeting the different energy demands of homes versus industries?
No, they are very versatile in the sense that all you need to do is to size your system. For a home system, a 5 kilowatt or a 1 kilowatt to 5 kilowatt would be sufficient actually. So, and if you are looking at an industrial system where much higher power is required, so you have to design your stack accordingly actually. So that is the reason why fuel cell stacks are available, from various capacities. You few watts also it is available, and large stacks are also available. The typical stack is about 100 and for a vehicle is about 115 kilowatt or something like that. So they do multiple stacks combined together to give 200 kilowatt or something like that for a heavy duty truck. For this Indian train that I was talking about, they have a 600 kilowatt fuel cell system actually. Basically, it is four stacks, 150 kilowatt each. They have utilized for making for running the train. So depending on the size, depending on the capacity required, you can size your fuel cell. They are very modular in nature. So all you have to do is to ensure you have enough number of cells. That's all. So for a 12 watt like a 12 volt system, you would require about 24 cells or something like that. And based on the number of amount of voltage and depending on your control system, you can size your fuel cell.
Ma'am, are there promising developments in portable or small scale PEM fuel cells for domestic use?
Not as a domestic use actually. So these kind of systems are they are available. See, currently, what is the major bottleneck is the availability of hydrogen for such applications. So their systems are available. Fuel cell technology is proven. Only thing is hydrogen availability has become one of the major thing. But now that the ministry having so much emphasis on hydrogen, there is national hydrogen mission. So many calls are there on green hydrogen development and all that. So we hope that hydrogen will be available freely, so you can develop all these system for various applications actually.
How do these PEM cells contribute to reducing carbon emissions while using in industrial applications?
See, as such, the emission from a fuel cell is only water actually, because you are combining hydrogen and oxygen. But to generate hydrogen, you would require power actually. So there you are using either water electrolysis as a technology or or reforming hydrocarbons as the technology. So there you require power. But then if you are using the solar or wind or any other renewable energy for your generating your hydrogen, so the whole thing becomes green actually. So that is how they contribute. Contribute to the zero emission or net zero.
Can you tell which challenge in fuel test cell technology do you think is the toughest to overcome right now?
See, if you look at the cost component wise, stack, like I said, they have more or less freezed about various components of the stack. Like this should be the amount, this should be the amount for that stack. But system, if you look at it, the system cost, BOP, balance of plant component, it cost itself is equivalent to that of fuel cell. So while lot of effort is being done on the materials and the various components, not much research is done on these kind of control systems and all that. So there is lot of scope there actually. Immediate scope is there. Materials, of course, there is always scope. Actually, you can always improve by in terms of efficiency, in terms of performance, in terms of lowering the platinum into the electrode or alloying. So many ideas are there in that. So, but here most of the component is not from the fuel cell manufacturer. They themselves buy from various other companies and integrate. So there is a lot of challenge there. And hydrogen storage, how do you transport hydrogen? I did not touch upon hydrogen storage and transport at all. So do you do a gaseous transport? Do you do on-site generation? Is it possible to do onboard generation? All these things are also important challenges.
How soon do you think fuel cells could be widely adopted in India, ma'am?
See, current bottleneck is the hydrogen actually.
Okay.
So now most of the, if you look at various systems, there are many hydrogen valley programs itself have been devised by Department of Science and Technology and all, where they have all utilization, develop generation and also storage. So such kind of hydrogen valleys, when they come, then it will become widely used. So currently, see, even though they have the Indian Oil bought 5 buses, and there are buses running in Gujarat. Reliance is running some of the buses within their campuses, and also in Leh Ladakh, there is hydrogen filling stations are coming up where they want to keep the ecological balance and all, not pollute the atmosphere. So all these things, although they are there, they are one off actually. Only one. If you currently, if you see, there are only some 3 filling stations in whole of India and things like that. So once all these hydrogen, by 2030, there are so many hydrogen plants are going to be fully commercialized. So like that, once it comes, I think there by 2030, 40, you should have many vehicles also, and also for backup power also, you will see a lot of fuel cell application.
What are the materials which are key for improving fuel cell efficiency and its lifespan, ma'am?
Catalyst is the main thing.
Okay.
Most of the research goes on how to make sure that the catalyst is stable. It does not get poisoned by the various atmospheric gases. You are using air from the atmosphere. The atmosphere has some sulfur dioxide, nitrogen gas, nitrous oxides, carbon monoxide. All these things are there. So all these things can reduce the efficiency of the fuel cell. So there are filters available, how efficiently you try to remove all these things, how well you make your catalyst immune to all these things. Those are the things that are those will are the challenges which, if you do, your efficiency will be more actually.
Finally, what advice would you give to our students who want to work in this field, ma'am?
lot of opportunities are there. Since with so many hydrogen companies coming up which are generating hydrogen, there are not many personnel actually who are trained in handling gases and all. So initially it was thought that the people who are already handling natural gas and all will be trained for first level of handling hydrogen and all these things. So a lot of opportunities are there, and being multidisciplinary, it can take up various disciplines actually. A lot of opportunities are there in, simulation. That is another thing that I have not touched upon actually. Lot of simulation work is going on to optimize the maximum and maximize the performances. All those are also very important. So being multidisciplinary, there is opportunity for everybody here.
Yes, ma'am. You are well said.
Yeah.
Participants, any questions from you? This is interactive session. Please ask your doubts. I invite Dr. Anisha ma'am to give Thanksgiving speech.
First of all, I thank Madam for accepting my invitation. And it's my honor to extend our heartfelt gratitude to Ramya ma'am for today's enlightening session. Your presentation on fuel cell technology, storage system, and their role in India's energy transition was truly inspiring. The clarity and simplicity with which you explained complex concepts made easy for all of us to understand. We greatly appreciate your insights on how fuel cell technology support India's net zero emission targets. Your examples and real-world applications made the session highly engaging and informative. The interactive discussion of our participants may be expected, and it gives us immense value to our learning. We are thankful for the time and effort you took to share your expertise with us today. Once again, thank you, Ramya ma'am, for this enriching session that has inspired us to explore fuel cell storage solutions further. Thank you, ma'am.
Thank you.
And I thank all the participants.
Thank all the participants.